All right, so this is the lesson on 4.9 impulse, right? And so we're gonna skip most of this now, but I do want to describe the GIF. So both cars start at the same velocity. They have the same momentum. When they hit the wall, their momentum reaches zero. So your change in momentum is more or less the same. So if you are changing your velocity, you have an acceleration, which means that there is a force acting on you. But how does the force differ when how does the applied force that acts on these test dummies differ? In both situations, you're coming to a stop. In both situations, you start with the same momentum, which means you require the same amount of force to stop both test dummies. But how does that force differ? What is different when there's an airbag and a seatbelt versus no airbag and a seatbelt? And that is the question, right? That's the do now. Well, what happens is that the airbag and the seatbelt help increase the amount of time it takes for your velocity to reach zero, right? Increases the amount of time it takes. So what happens is that then, well, the longer it takes for you to come to a complete stop, well, the more that force is going to spread out over the amount of time. And so let's take a look at this slide, right? So when you apply a force over a greater length of time, you change an object's momentum. You reduce the average impact force. So let's take a look. Let us take a look. Right, let's take a look. I want you guys to focus on the bottom left GIF, right? So I want you to focus on that. So let's take a look. Where is huh? Let's see my oh, I see it now. Anyway, oh, I'm on the wrong slide. Bottom left hand GIF, bottom left hand GIF. Please don't mess up on me. Cool. So let's compare the egg being thrown at a wall, right? Let's compare the egg being thrown at the sheet. You'll see that, let's say hypothetically, this is the wall, right? This is the wall. And you throw an egg at the wall, and so it says, let's say you use a force of, I don't know, 100 newtons, right? So you throw this egg at the wall with a force of 100 newtons, and the egg stops with a force of 100 newtons. So the wall applies a force of 100 newtons on the egg. And this all happens in 1 millisecond, right? Very brief, 1 millisecond. Well, what happens when it hits the sheet? Let's say it takes, I don't know, 10 milliseconds to stop. Let's say it takes 10 milliseconds for the egg to stop, to come to a complete stop. Well, what happens at that point is that your force becomes spread out, right? So let's say, well, for the first millisecond that the egg hits the sheet, well, you experience a force of 10 newtons. And the second millisecond that the second millisecond of when the egg hits the sheet, well, there's another force applied of 10 newtons, and so on and so forth. And so this goes on until 5, 6, 7, 8, 9, 10, right? And so there's a force of 10 newtons applied each millisecond, and so on and so forth, right? So there's 100 Newton force that would have been applied to the egg when it hit the wall in 1 millisecond. Well, if it takes 10 milliseconds for you to have a force of 100 newtons, well, then you experience less force each second, and so the egg doesn't break, right? So if you have 10 milliseconds to apply a force of 10 newtons each millisecond. Well, all of these add up to 100, right? Right, each millisecond, if you're applying a 10 newton force each millisecond, well then that adds up to 100 newtons. And so the force applied by both wall and sheet are equal, but the difference here being that in one situation you have a greater amount of a time, right, for your object to come to a complete stop. And that is crucial. That is very crucial. And so this, and obviously it doesn't work like that in real life, right? That I just told you as like a very simplistic explanation. But if you take a look at the bottom right hand GIF, right, that's actually how it would behave in real life, right? You kind of have at the beginning it's very low amount of force, and then as time increases, right, you come to a peak amount of force, and then as the object comes back up, well then, well, you don't have that much force anymore, right? And so again, as you let's take a look at the top right hand image. If you extend the time of collision, well, you reduce the amount of impact force, right? You reduce the average impact force, right? So let's explain the formulas on the left. Right, you have F net T. So it's essential, right? The force applied over a period of time is equal to your change in momentum. And your change in momentum, your delta P, right? Because the delta means change. And the momentum P is momentum, right? So delta P is your final momentum minus initial momentum, right? Which is essentially a mass times final velocity minus mass times initial velocity. And so then this also, because we also know that delta V is equal to Vf minus Vi. Well, we can simplify this, right? Mass Vi, we can just essentially do that. And then we can just treat like that, right? And then we can say, well, F net T is equal to M delta V. But the only thing you actually need to remember is this, right? And then this. You don't really need to remember anything else. You just need to remember these two. I mean, they're all in your reference table. Let's move on. So we're going to move on to impulse. Again, impulse is your change of momentum of an object after a net force is applied over a period of time. So impulse, right? Impulse is J and is equal to delta P. And so when you come next to it, this is on your reference table. This is explicitly on your reference table, right? So J impulse is equal to net force applied over a period of time is equal to your change of momentum, right? And that's essentially what it is. It's essentially A is equal to B is equal to C, and then we can do like, well, A is equal to C, right? And that's essentially what we can do. All right, and that's a formula. And again, when let's talk about the top right hand GIF, right? If we're taking a look, so if we think about it, when we're engineering cars, we want to make sure that the car does in fact break. We're not trying to make an invincible car. We're not trying to make an invincible truck. There's no point to it, right? Because the passenger themselves will die, right? Because you keep going forward. Sure, the car might not break, but you keep going forward. Right? If you think about if you've ever been in a car or a train, right, and they stop abruptly, well, you kind of keep going forward a bit, and your seatbelt stops you. Well, this is essentially what's happening here, right? So what happens is that engineers, when they're designing cars, they want to make sure that your car takes as long as possible to reach a velocity of 0, right? So which is why they designed the hood of the car to make sure you see this crumple, right? Make sure that this hood will take the longest amount of time will crumple really well. So it increases the amount of time it takes for you to get the momentum to 0. And the airbag and the seatbelt, they essentially increase the amount of time it takes even further, right? Your airbag is actually really like it's soft, but that's besides the point. The airbag increases the amount of time it takes for you increases the amount of time it takes for the force to be applied, right? And a few milliseconds is the difference between you living and you die, and that's all it takes. Now, you can watch this video by yourself. I can't play it because it's copyrighted. You should. I recommend you that you watch this video, right? So you just go to Google Slides and watch it. But I'm not gonna play it. So let's do some practice questions. And let's do some practice questions right here. All right. So you have a 1.0. You have a 1.20 times 10 to the third kilogram car. You're traveling east. So you have initial velocity of 25 meters per second. The brakes are applied. The car is brought to rest. Since you're saying car is brought to rest, it's 0. Your final velocity is 0. Your time is 5 seconds. And then they also say calculate the magnitude of your total impulse. So they want impulse. They want J. Right, so we learned J is equal to F net T is equal to delta P. We don't have force, but what we do have is we have our impulse and our delta momentum, right? So our change of momentum. So we're gonna use this. So J is equal to final momentum minus initial momentum. J is equal to mass times final velocity minus mass times initial velocity. So mass is 1.20. Well, this entire thing right here is 0 because your final velocity is 0. So let's save some space. 1.20 times 10 to the third. And your initial velocity is 25. Right, so you continue solving this. This gets you, what does it get you actually? 25, 30, right? So we get 30. I mean, we don't get 30, but we get 3 times 10 to the 4 Newton seconds, okay? That's what you get. Okay. So you have the 3 kilogram object. So your mass is 3 kg. As acted on by an impulse having a magnitude of 15 Newton seconds. So your impulse is 15 Newton seconds. And the question is, what is the magnitude of the object's change in momentum? And so we're asking you, what is your change in momentum? So what is delta P? What is your change in momentum? Well, if you think about it, impulse is equal to F net T is equal to delta P. And we know that J is equal to delta P. Which means that 15 Newton seconds is delta P. And that's it. That's the answer, right? Your literal definition. The literal definition of an object's change in momentum is your impulse. That is impulse. Impulse describes your change in momentum. That's it. That's the question. No math needed. Let's do this question. So you have a 1,000 kilogram car, right? So your mass is 1,000 kilograms, traveling at 20 meters per second east. It's 20 meters per second east. Experiences impulse of that. so its initial velocity, has an impulse of negative 2,000 Newton seconds, right? Because it says west, right? Going the opposite direction. And the question says, what is the final velocity of the car after this impulse has been applied? So what is Vf? So we use this, right? So we don't have force, we don't have time. So what we're going to do is we're just going to do J is equal to delta P. J, the final momentum minus initial momentum. Mass, final velocity minus mass, initial velocity. Right, final velocity is question mark. That's what you want to solve for. Actually, J is something, right? J is negative 2,000. Mass is 1,000. You want to find out that. Minus mass is 1,000. Initial velocity is 20. Just keep simplifying. Minus 1,000 times 20 is negative 20,000. Just plus 20,000 here. Plus 20,000. You get 18,000 equal to 1,000 divided by 1,000. We get 18 meters per second. And that is the final velocity of the object. 18 meters per second. Okay? I mean, here's like, okay. Right? Again, impulse is your change in momentum. Essentially, if you apply an impulse, well, you're changing the object's momentum, which is why the velocity of the object decreased. Alright, so you have a 75 kilogram hockey player traveling across the ice with 6 meters per second. What's the magnitude of the average force required to stop the player, right? So the final velocity of the player is 0 in 0.65 seconds, right? So here is the thing. So we have our formula. Our impulse is F net T is equal to delta P. We have our force, we have our time, and we have delta P. So right, we don't need J. So we were just cut that out. We don't have impulse, so we just getting rid of J. So F net is what we want to solve for. T is 0.65 minus pi. You separate this. Minus mass, initial velocity. Final velocity is 0, so this entire thing here is 0. Minus mass, 75. Initial velocity is 6. Uh, 75 times 6 gives me negative 450. And then divided by this. And we get 4. Not only 2 newtons, okay? Well, it's negative, but the question is just asking you for the magnitude, right? The question is just asking you for magnitude, which means they don't really care about direction. They just want the number. It doesn't matter if you put negative here or not. All right. Last question. You have a You have a mass that's 0.149 kg. Initially moving at 15 meters per second. Is brought to rest. So initial final velocity 0 in this amount of time. The magnitude of the average force exerted on the bar. Exerted on the ball. Alright. So you have that. So again, we don't have impulse, we don't have J, so we're just gonna do this, right? So this is the form we're gonna use. So F net T 0.04. Delta P, again, it's like mass final velocity minus mass initial velocity. Final velocity is 0 minus mass is 0.149. Initial velocity is 15. 15 times 0.149 is negative 2.235 divided by 0.04. And our net force is somewhere around 56, right? So negative 56. But again, they don't care about the magnitude, so they don't care about direction. So 56 newtons is fine. Okay.